Welcome everyone to this new video. In this new video, we're going to learn about streamflow measurements. Uh, in the last video, we finished covering everything related to hydrographs, and now we are getting into a new chapter, which is related to how to measure the stream flow of a river channel or a pipe, any type of uh, water flow. So for this video, we have three problems, and let's start with 7.1. 7.1.1 says recalculate the discharge for example problem 7.1 if the area of section 4 were doubled. The example problem is here. This is the data given in the example problem 7.1. It says for a particular stream, estimate the flow rate using the following data for velocities measured at two depths, 0.2 and 0.8 of the total, and the cross-sectional area corresponding to the velocity measures. So all we need to do here, I'm going to explain it. We need to change the section 4 here. We need to double that and we need to make it 16. I have it down here already where I have doubled this value from 8 to 16. Um, and let's solve it, and then I'm going to explain these graphs here that I have. These are velocity profiles, but the way you solve this problem is all you need to do is find the average at these two depths at 0.2 and 0.8 of the depth, and then multiply by the area. This will give you a meters per second average. Multiply by square meters, gonna give you cubic meters per second. That's all you need to do for this problem. Equals to the average of these two values multiplied by the area, the cross-sectional area. And we do the same with the rest of the sections. And then all we need to do is sum up all these values. And this is cubic meters per second. This is your answer here. Now, before we move on to the next problem, I want to explain really quick why we measure the velocity at 0.2 of the depth and 0.8 of the depth of the river. This is a velocity profile here. This is as if you were looking at a river from its side, from the side either right or left. So let's say the water is flowed to the right direction. So it's coming from this end to the right. The velocity of the water is gonna be higher closer to the surface. Let's say this is the surface, and going down you go deeper into the river. So the closer you are to the bottom of the river or the channel, there is more friction, so the water is gonna flow slower than the water closer to the surface, where it's farther from the bottom. There is less friction. So this is the shape that it forms, the velocity of the water forms when you take data values at each depth, and it can be generalized by this graph right here. It's a rough approximation of what the velocity of the water is flowing downstream, in this case from left to the right. This is seeing it from a side. Now if you see it from the top, like if you are in a, I don't know, watching the river from a drone or just from above, this pretty much gives you the velocity of the water at different phases. But once it's fully developed, you can notice that the water flowing at the center of the channel is going faster. Think of the arrows as the magnitude of the velocity. So the arrows at the center are longer than the arrows closer to the banks of the river. So this is pretty much the shape of the velocity of the water in a river. So if you see it from the side, it's faster at the top, slower at the bottom. If you see it from above, it's faster at the center, slower on the sides, closer to when you're closer to the banks. Now, if you want to see it from, let's say, this have another image here. Let's move it up here. Let's say the water is, you are right in the river, in the river, and the water is flowing at you This is pretty much how you will understand the velocity profile of the river. So combining the previous two graphs, you will say that the velocity of the water is faster at the center and at the top. Here, this is an example, 1.9 meters per second, and it's slower when it's closer to the bottom. So you will see this, an exercise similar to this graph in the next video, or what will be the next video. But this is just so you understand that velocity in a river channel varies depending on where it is in the channel. So that's a conceptual part about water flow velocity. Let's move on to the next problem. 7.2. It says imagine a rectangular channel with water flowing through it. We have placed a barrier called a weir across the channel to measure the flow rate. The weir is 3 meters wide and has end contractions which affect the flow rate. We have data about how high the water level is, or the head, on the weir at different times. The task: create a graph that shows how much water is flowing through the channel over time. This graph is called a flow rate diagram. So a weir is, I have a couple pictures here, um, so you can contextualize yourself on what we're doing here in this problem. So if you remember from the previous problem, we are given the values here of velocity to calculate the flow, and you saw how easy it was once we're giving all the values and the area and everything just to plug in. However, sometimes it's not as easy to know what the width varies here depending on the channel and the form of the channel. So to normalize this, we can create a weir where we have we already know the width of the opening, and then all we need to do is calculate the height here through the opening. So we go from a varying shape into a shape that we are more used to, um, and it's gonna be easier to calculate how much water is flowing through this opening. Now, it's not as simple as multiplying the opening times the height of the water. We have a equation here that is being derived in approximates better what's the flow on a weir channel with contracted sides with contractions. There are different types of weirs, which depending on the weir, you might want to use a different equation to solve for the flow of water through that weir. So this is the one of the main reasons why weirs are used, is to measure the flow. It makes it easier to measure flow. That said, let's move on to solve the the problem. So we are given the data and we are given the head, which head, what it means, all it means is like the height of the water. If you see here, it will be the height of the water here right over the opening. If you follow this line here in this graph, is right over the opening up to where the water is flowing. So we're giving all those values, but we are giving those values in meters. Now you can solve this equation with the values in meters. The only difference would be that the weir loss coefficient, it would be 1.84 for meters. But if you want to solve them for feet, you want to use 3.33 for feet. Now you can solve it for meters, but the book solves it in feet. So let's make the conversions of this head from meters to feet. I have already done it. If you want to remember, 1 meter equals 3.28 feet. So all I have done is multiply each value here by 3.28, each of these values. And that's how I got all the heads in feet. Now to solve for the flows, all we need to do is apply all these heads into this equation. I have it here as well. And remember that the base is 3 meters, but we're working with feet now. So we want to multiply those, the value of B of the opening. We want to multiply is 3 meters times 3.28 to get it in feet. Now with all our values in feet, we can solve for each flow at each time period. So this is going to be 0, and this is going to be equal to the coefficient, the weir coefficient in feet. It will be this, and we wanna absolute that times h, which is the head in feet, to the 3/2 times the opening, which is 9.84 feet, and we want to absolute that as well, minus zero point 0.2 times the head again. So that gives us this value, and hopefully if we drag it all down, we get these values in CFS, which I think they seem right. I think I did it correct. Let me double check really quick. And 13, that's the coefficient. C17, that's the head value, times to the 3/2 times J12, which is the opening, minus zero point 0.2 H, which is the head again, C17. Okay, and that should be right. All we need to do now is create the graph. And what I'm going to do is select the data, insert chart. Now we have the head and the flow here, but if you notice, the values of flow are much higher than the values of the head in feet. So we want to create a two-axis graph so we can see both series. And the way we do it, and I found it, change this to this, and then I click on the series, and then I go to series, and in axis from left you do right, and yep. So in here you can see the values of the head from 0 to 4, which is the blue line, and then on the left you can see the values of the flow from 0 to 250 in CFS. So you notice that both follow a similar pattern, and it makes sense that if the head or the height, let me close this, if the height of the water flowing through the weir is higher, that means there is more water going through, and they both are related, very 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 similar shape. So I believe this is it for this problem. Create the flow channel. This graph is called the flow rate diagram. So that's what we do. And now let's move on to the last problem of this video. 7.3. For the catchment that produced the flow rate diagram for problem 2, the previous problem, the land use was changed in a 1,520 millimeters concrete pipe on a longitudinal slope of 0.05 replace the open channel. So instead of having a open channel now, that was replaced for a concrete pipe that is gonna drive all that water downstream. Concrete pipe that might look like this that I have an image here. So probably it was changed by that. Um, Now we are asked to graph the flow rate for the storm event that produced the following pipe flow depth, area, and hydraulic radius. Assume flow rate starts at time 0. Now, for this problem, we are given the flow depth, flow area, and hydraulic radius. All hydraulic radius is the cross-sectional area divided by the wetted perimeter. So the weather perimeter is like, let's say if we take this pipe here, concrete pipe, and if the water is not going full, let's say it's going halfway, the weather perimeter would be like the length of the says cross-sectional area, and the weather perimeter would be like the part where the concrete is wet, like the water is touching the concrete. So if it's halfway, it would be just the bottom part. So you divide the whole cross-sectional area divided by what the water is touching. Um, However, we are already given the values, the hydraulic radius here. So all we need to do is plug all those values in the Manning's equation. Now, the Manning's equation requires four parameters. One is the n value of Manning equation that you can find it in table 7.3 that I have here. The hydraulic radius, the area, and the slope. Now we are given the slope of the pipe and it's 0.05. I have it here. Slope is represented with a letter S. Um, and then we are given the flow area as well. And the hydraulic radius were also R is the hydraulic radius. We're also given that. So we actually will not need this value of the diameter of the pipe because we are already given the hydraulic radius. If we were not given the hydraulic radius, we will have to estimate it by using the flow depth and knowing and finding out the cross-sectional area. But they already given us this value, so we don't need to solve for that. Um, so all we need to do here is use the Manning's equation to solve for the flow at each different time period. So the first one is gonna be 0, and then we're going to do 1 over n equals 1 over n. Oh, let me explain where I get n from. So n is 0.013. And we have the roughness coefficient value for the Manning equation. We have we have it for closed conduits flowing partly full, which is A in this table, and B for channel conditions. In our case, it's a pipe, it's a closed conduit, and the water is most likely flowing partly full. It's not completely full in the pipe, and it's made out of concrete. So we go to letter F, and we're assuming a straight pipe, so which would be the covered concrete. So we have three options here: minimum, normal, and maximum. If we assume that the concrete pipe is new since it was just changed, we should use 0.013. Now, I think this is like an approximation of the time, how long it's been the pipe used, because since water is been going through, its roughness coefficient is gonna be decreasing over time, because water is gonna be smoothing the surface inside of the concrete pipe. So since it's just new, we're using 0.013. So that's how we got that value right there. So we have 1 over 0.013, then multiply by the hydraulic radius, which is 0.38 in our case here. Oh, times hydraulic radius for the value of 20 minutes. Uh, all of that to the 2/3, 2/3. And then let me put this in parentheses just to be extra careful. And then all of that multiplied by the area, the flow area, and then multiply by the slope. The slope, let's absolute that to the 1/2. Um, Hopefully I did this right. Area, slope, 1/2. Yep. So we got the value for here. Then if we drag it, we should get all these values. And all we need to do now is just plot these values. And I have it here vertically. So we have time in minutes, 0, 20, 40, 60, 80, 100. These are the times here. Now, if you notice something, by using this equation, you get CMS, or cubic meters per second. Now, we get a flow rate, even though we are not using seconds, or technically we're not multiplying any times in here. So that's something interesting that you might wanna look into it. It was the same here. We are getting CFS from this equation. Like the rate of water is involved in that equation. Um, all we need to do now is this is equal to this, pass those values here. And the reason why I do this instead of just plotting from here is because the spreadsheet requires columns. At least that's the error that it gives me when I try to do it directly. So it's not very, uh, doesn't make your job easy actually. But now that we have these values here, all we need to do is plot it, and you do insert chart, and you get a plot like this. And this should be enough for the answer of this problem. The values found using the Manning's equation and the plot of those values of the flow um, for this problem. So this is it for this video. I hope you find this helpful. I will actually stop making videos this semester here. This will be the video number 20. I am getting very busy with my own schoolwork, and I think it's just better for me and for my own sanity to use the time that I spend making these videos on my own coursework. I do plan on finishing. There are 7 more videos planned for this series. I do plan on finishing by next semester. So if you are studying hydrology next semester, you should be finding the rest of the videos by then. The rest of the videos are related to how to keep finding the flow in rivers, how to find the velocity. Uh, in this problem, we were given the velocity. Now the next problems are gonna be related to how to find that velocity. What else? And then farther down, later we're gonna be also seeing more stream flow. We're gonna cover flow routing. We're gonna learn more about that, and then we're gonna get into groundwater. So we are done with what is it, hydrograph so far. Now we're going into a little more of finding the velocity, the flow velocity, and once we're done with that, we're gonna cover groundwater. And after that, we have covered every single basic, I would say, all you need to know about hydrology, hydrologic engineering. And with that, you should be in a very good shape to move on to a higher level hydrology analysis. Um, with that said, if yeah, good luck solving these problems, and I hope I see you in the other videos. What I'm planning to do after finishing this hydrology series is to work on what is CE 304 and 306, which is metals, woods, and composites, and concrete design. So I'll work on making a series of videos for that one as well for the next semester. So yeah, good luck and see you later. Bye bye.